So last lesson, we briefly talked about the fact that if you move a particle through an electric field, then you have to do work to it to move it, okay? So we said that this positive charge, if we move it over here, we're doing work. We have to go against the electric field, we're doing work. When we hold it there, we've done work to get it there. As soon as we let go of it, that work done will all change into kinetic energy because it'll ping back, okay? So similarly with the gravitational field strength, so you lift something up and you're holding it in place, it's got gravitational potential energy. As soon as you let go of it, it moves into kinetic energy, okay? So, potential energy and kinetic energy. So when a charged particle is accelerated by an electric field, the work done by the electric field, or the potential energy lost by the charged particle, is converted into kinetic energy. So kinetic energy equals work done equals Q times V, which is the equation we came across last time. So the speed of the accelerated particle can then be found using your regular equation. Kinetic energy is half mv squared. So, example 1. We've got a positive charge of 3 microcoulombs is moved from A to B. The potential difference between A and B is 10 volts. So part A says calculate the electric potential energy gained by the charge field system. So basically that means the potential energy gained is equal to the work done moving that charge from A to B. Okay? And remember, the work done is the charge times by the voltage. So the charge, we're told in the question, is 3 microcoulombs, so 3 times 10 to the minus 6. And the potential difference between A and B is 10. So the work done is 3 times 10 to the minus 5 joules, and that is the electric potential energy gained as you move it from A to B. The potential energy is the same as the work done. Okay, and you were doing questions on that not last lesson, the lesson before. So B says the charge is released. Describe its motion. Well, we were talking about this before. We move this over here, we hold it there. As soon as we release it, it moves back towards the negative. But is it a constant speed or is it an acceleration? Acceleration, yes, because it's got an unbalanced force. Okay, so the charge experiences an unbalanced force so accelerates towards A, so basically back towards A. Okay. So we've given it some energy, we've done work to move it towards the positive, then we let go of it and it moves back to A. Okay, so just like the gravitational field strength, you've done work to lift it up, you let go of it, it all changes into kinetic energy. Same happens here. So you've done that work, it's all stored as electric potential energy. As soon as you let go, it all moves eventually into kinetic energy. Okay, so no idea what's going on there. So basically, the kinetic energy is equal to the work done. So 3 times 10 to the minus 5 joules. Okay, so you can write in brackets just to remind yourself. You don't need to write this when you're answering questions. The electric potential energy all transfers to kinetic energy. Obviously, there probably will be some lost, but due to, well, some transfers to sort of it's much less likely to any energy sort of transfers to heat due to friction in these kind of situations than there is in like a rock being dropped and things like that. Okay. So have a read through the next one. I'll leave that for a little bit longer, but have a read through the next one. For the next one, basically you need to know some information. You would look them up in your data sheet if it was given to you as a question in a test. But you do need to know a couple of things that I will write down. So has everyone got that? Right, so an electron is accelerated from rest by a 2 kilovolt supply connected across 2 plates in a vacuum, as shown below. Okay, so first of all, it says calculate the work done by the electric field on the electron. So basically, the electric field could do work as well. Okay, then it's just the same, work done equals charge times voltage. Okay, so for this one, obviously you're not given a charge, but you are given that it's an electron. So you would look at your data booklet and you would find the charge on an electron, which is 1.6 times 10 to the minus 19 coulombs. You'll probably also later on in the question need to know the mass of an electron, which is 9.1 times 10 to the minus 31 kilograms. Okay. As I said, those values will be in the data sheet in the test, but they won't necessarily be in the question. So if you ever have a question like this and you think it's not giving me enough information, it may be that you need to go to the data sheet to find the information. Okay, so it's not going to be as straightforward as in National 5 where they give you all the data. In higher, sometimes you have to go and find it from the data sheet. So now we have found that from the data sheet the charge on an electron, we know the voltage, we know the potential difference is 2 kilovolts, so we just need to times them together. So 1.6 times 10 to the minus 19 times by 2,000 or 2 times 10 to the 3 volts. And that comes to 3.2 times 10 to the minus 16 joules. B says find the kinetic energy gained by the electron. So we now know that the work done by the field is equal to the kinetic energy gained by the electron. So kinetic energy is equal to the work done. So 3.2 times 10 to the minus 16 joules. And C is relatively straightforward. Find the speed of the electron at the positive plate. So now we know the kinetic energy gained. So we know what the kinetic energy of the electron is. So we can find the speed from the kinetic energy equation. So EK is half mv squared. So 3.2 times 10 to the minus 16 equals half, times by the mass of an electron, which you find from the data sheet, 9.1 times 10 to the minus 31, times by the speed squared. If you work that out, you end up with a speed of 2.65 times 10 to the 7 meters per second. Now, in higher, they might not split that into A, B, and C. They might just say, here's the information, what's the speed of the electron at the positive plate? Okay, so you might have to do it all in a one-er. So you'd have to find the work done. You know the work done is the kinetic energy gained, and then half mv squared. Okay, so it might not necessarily be as straightforward step by step as that. It might just be a quick one question, like maybe a 5-mark question, find the speed. So you've got to do it all in a one-er. But those are the steps that you go through in any kind of question like this. All right, have a read through example 3 as well. I'll leave that up, don't worry, but have a read through. Example 3 is probably a diagram you've seen a few times before in the past when you've been looking at electrostatics and cathode ray tubes, but you won't have done it in this much detail before. Am I okay to move on? Yep, okay. Right, so the electrons which are emitted from the cathode start from rest and reach the anode with a speed of 4.2 times 10 to the 7 meters per second. Okay, so basically what we've got is we've got electrons just here, they're at rest, then they get accelerated towards the anode, okay? And when they reach the anode, they have a speed of that 4.2 times 10 to the 7 meters per second. So A part I says calculate the kinetic energy in joules of each electron just before it reaches the anode. So basically it means as it reaches the anode. So what is the kinetic energy at this speed? So you can do that one relatively easily. So kinetic energy is half mv squared. So again, we're going to use mass of electron, we defined in our data sheet as 9.1 times 10 to the minus 31 kilograms. We'll also need at some point the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. Right, so we can do the first one, nice and easy, kinetic energy equation, half times 9.1 times 10 to the minus 31 times by that speed squared, 4.2 times 10 to the 7 squared. Can you all please put that into your calculator? Make sure you can do your indices correctly in calculator mode. Should be getting an answer of 8 basically times 10 to the minus 16. Sorry? So make sure you're getting that answer. Because generally in these kind of questions, they're relatively simple theory, but because there's all the minus to the 10s to the minus 31s and 10s to the 7s and squaring them, then quite often people just make mistakes by putting things into their calculator wrong. So just make sure you are happy with putting things into your calculator and you're getting the right answers. If anyone isn't, please let me know. Okay, question part A, part 2 says calculate the potential difference between the anode and the cathode. So we know that the kinetic energy gained between the cathode and the anode is the kinetic energy is 8.03 times 10 to the minus 16 joules from part 1. Okay, so we also now know that the kinetic energy gained is the same as the work done between the two. Okay, so kinetic energy gained is equal to the work done. So EK equals W equals QV. So EK from part 1, 8.03 times 10 to the minus 16 equals Q, it's an electron, so it's charged on an electron, times by the voltage. And you should end up with a voltage of 5,000 volts, sorry, it's 5,019 volts, so 5 kilovolts. So again, if you think that the question hasn't given you enough information to work it out, chances are you need to go to the data sheet and find the things. Okay. And part B, describe how the spot at the center of the screen produced by the electrons can be moved to position X. Your answer must make reference to the relative sizes and polarity, so signs, of the voltages applied to plates P and Q. Okay, so we have seen this kind of thing in the past. So basically what is happening is we've got the electrons, they're being accelerated and they're fired up here. Okay? And if they go straight on, they end up right in the middle of the screen. But we can move it up and down, or left and right, by charging these plates. So if we want it to go up one, then we would charge P positive, so it would attract the electron one. Or we could charge this bottom one negative to repel it up. But I tend to just go right P. We'll charge that positive, it will go up one. Okay, so that's it gone up one. But we also want it to go in that direction Q. Okay, so we need to charge Q positive, but twice as positive as P. So I've got up one and along two. Does that make sense? Yep, so we need to write that down. So we need to charge both P and Q positive. Q must be twice as positive as P. That's what it means by relative sizes. It means that Q's double P, basically. So up 1, P is 1, and then along 2, Q is 2. One more example after this, and then I'm going to get you guys to do questions. And example 4 is a wordy question. So feel free to have a read through it first of all. Okay, right. So describe and explain the motion of the negatively charged particle as it passes between the plates. So this is a particle, it's moving in that direction, but and then it hits the field, okay? So it moves into this field where it's positive at the bottom and negative at the top. So basically, the movement that it will follow is like that. So what is that? That's quite familiar, that sort of shape. Projectile, yeah. So what it says, describe and explain the motion of a negatively charged particle as it passes between the plates. So to explain it, we explain it just like we'd explain why does a projectile move in that way. So we can say the particle experiences an unbalanced force towards the positive plate. It will accelerate downwards. Just like in a projectile, whatever you project experiences a constant acceleration down the way because of gravitational field strength. In this case, it's experiencing acceleration downwards because of the electric field strength rather than the gravitational field strength. But also, particle has a constant horizontal speed. It will curve downwards. Like a projectile. Okay, so you can see again there's a bit of parallel there between gravitational field strength and electric field strength. Okay, we've never drawn the gravitational field strength to having lines and things like that, but it kind of works the same kind of way. So we've got this constant acceleration downwards due to gravity, okay, due to the gravitational field strength. We've also got a constant horizontal speed, just because of the way that it's fired. Yeah, so it works kind of similar way, just like gravitational potential energy and electric potential energy. Right, okay, question booklet. So you did page 1 the other day. So now I would like you to work your way through pages 2 to 5. Okay, you can skip some if you want to sort of do a couple from each page and make sure you're happy with them.